That last video was a little thick. This one's going to be a little bit easier. We're going to talk about right triangles today, these triangles that have a 90-degree angle in them. And this is going to be another way that sine, cosine, and tangent can relate angles to distances. All right, so one thing that you definitely remember about right triangles from high school would be your Pythagorean theorem, right? So this is where we labeled the side lengths A, B, and C. And then the Pythagorean theorem told us that a squared plus b squared is equal to c squared, where c squared was always the long side length that's across from that right angle. We call that the hypotenuse. All right. If you're a history buff, you might want to look up Pythagoras and his odd cult of mathematical followers. They were really kind of an interesting group. All right, but we have their Pythagorean theorem to use when we have a right triangle. Let's do some more terminology for right triangles. Right, so I said that the long side of the triangle, a right triangle, is always going to be called the hypotenuse. So let's spell that, hypotenuse. All right, now I've thrown this angle in there, that angle theta, and the other two sides are going to get names in relation to that angle theta. Right, so the angle theta, the little swoop up there, is touching the hypotenuse, but it's also touching that vertical side. The vertical side that little swoop is also touching, we call the adjacent side. That side is adjacent to the angle. And then the third side that the little swoop is not touching, we call the opposite side. All right, and our trig functions, it turns out, end up being ratios of side lengths of right triangles. Okay, so the sine, and this is the same sine that we know and love from our unit circle, the sine of that angle theta that's up there in the right triangle is always going to be equal to the opposite side length divided by the hypotenuse. Right? True for any triangle that angle is in. It's the same sign that shows up as the y coordinate on the unit circle. All right, and then the cosine of that angle is always going to be whatever that adjacent side length is divided by the hypotenuse. And then the tangent of that angle is equal to the opposite side length divided by the adjacent side length. All right. And we usually remember these relationships with the acronym SOHCAHTOA. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So SOHCAHTOA, that's usually how most people remember these relationships. I did once hear some old hippie caught another hippie tripping on acid. I don't know. Anyway, SOHCAHTOA. All right, so it turns out that this SOHCAHTOA right triangle trigonometry completely gels with what we learned about the unit circle. So remember in the unit circle, we would draw this angle theta and we had this terminal point x comma y. So we can impose a right triangle on here to see this relationship. So I'm just gonna drop a perpendicular to the x-axis so that I get a right angle and a right triangle that includes the angle theta. All right, so remember what it means to have those coordinates, right? If I x coordinate, whatever it is, that's this distance here. That's going to be the adjacent side of my right triangle. The y coordinate has to be this distance here, right? Because that would be our y tick mark up here. This would be our x tick mark down here. All right, and then the hypotenuse of this right triangle, well, it's in the unit circle, right? It's inscribed inside there. That's just a radius of the unit circle, which we know is always 1. Right, so if I use my new definitions of sine, cosine, and tangent with this green right triangle, sine of theta, I said, was opposite over hypotenuse. So the opposite side is y. The hypotenuse is 1. Cosine is adjacent over hypotenuse. All right, and then tangent is opposite over adjacent. So that would be my y over x. Okay, those are exactly the definitions of sine and cosine and tangent that we had with the unit circle, right? Sine is equal to the y coordinate, cosine is equal to the x coordinate, and tangent is then equal to sine over cosine. All right, these are exactly the same trig functions. We've just put them into right triangles. One more connection I want to make with our unit circle values and these right triangles. We'll just use 30 degrees as an example. I know from my unit circle that sine of 30 has to be equal to 1/2, okay? So any triangle that's got 30 degrees in it has to satisfy this, that the sine of 30 is equal to 1/2, because that's always the case. The sine of 30 is equal to 1/2. So if I think about this as opposite over hypotenuse, it's not necessary that every triangle in the universe with a 30-degree angle in it has to have an opposite side length of 1 and a hypotenuse length of 2. It just means that the ratio has to be 1/2. That means that this opposite side has to be half as long as the hypotenuse. So this could be a triangle with a 10 and a 20, or 100 and a 200. As long as the hypotenuse is twice the length of the opposite side, then you're going to get sine 30 equals to 1/2. And it would be impossible for you to draw any triangle, even if you drew, let's see, if I made this 15.5, if you drew a 30-degree angle with an opposite side that was 15.5 centimeters long, the only way to accomplish that is with a right triangle with a hypotenuse that would be twice that length, that would be 31 centimeters long. Okay, so these ratios have to hold, and they have to jive with what we know about these angles in the unit circle. All right, so we'll use the Pythagorean theorem and our new SOHCAHTOA definitions when we get together in class.